All right. Welcome back, everyone. We'll be starting. Uh, yeah. For the people who are newcomers, who are we? We are a bunch of physics graduate students at UWM working on various topics in astrophysics, having very little to do with what we talk here about, but fun ideas. Talking about fun ideas, if someone has a fun idea they would like to listen about, or any aspect of science, may it be astrophysics or something else, please feel free to contact us or catch any one of us and tell them, or just write it on a paper and throw it at us, whatever is comfortable with you, just so that the idea reaches us. And if you happen to be in or around Madison on December 17th, there is one more outreach talk by our friends at UW Madison. If you're interested, please feel free to attend that. With that said, uh, these are today's speakers, and the topic we'll be talking about is cosmic clutter. But more simply put, we're talking about satellites and space debris. So what are satellites? So the derivation comes from a Latin word called sattles, which means one who escorts or follows an important person. In this context, the important person is Earth. And then if we look at, is there something following Earth? You'll see a bright object at night that's following Earth. That's colloquially called as the natural satellite, but that's not the topic of the talk today. Today we'll be talking about something is broken. Sorry about that. Yeah. But today we'll be talking about artificial objects that are put up in space. So if you ever have Googled about satellites, you'll find that there are a large variety of satellites. There are satellites that we use for telecommunication. There are satellites that we use for tracking. There are satellites that we use to do science, earth science, weather science, ocean science. There are satellites that we use to do astrophysics, that's what we usually do. But the most important question is, why do we need to put anything up there? What are we achieving by putting anything up there that's not possible from ground? So if you just take a look at it, one example comes from communication satellite. I was told that this person is Walter Cronkite. I'm way too young to have physically verified this fact. So take me for a fact that this is Walter Cronkite. So what this is set in year 1962. So in 1962, there is no instantaneous communication between two continents. So let's say if I'm in US and if there is a person in, say, Europe, there is no text messaging, there's no video calling, and there's no internet. So how do you establish a communication in this case? So what's happening here is, shown in the right are a bunch of names of cities. So what's Walter Cronkite doing here is he's checking if the cities can receive a message. So he's calling out the name of each city, and then from the other end, they are saying if the message is received or not. How is this achieved? This is the same animation from 1962 explaining how is this achieved. So here we are in US, and there is a satellite up there in space. What is happening here is a message is being relayed from US to a satellite, and then the satellite is receiving it, and then it's relaying back to Europe. So that's how communication is established between two continents. So this is very common nowadays. So nowadays we use satellites like this for internet, for video calls, for audio calls, for live broadcasting, World Cup events, Olympic events, international politics, a lot of things. The next example, or the most commonly used thing, is navigation satellites, or more simply put, the GPS you use on phone. So you are essentially using your phone to track your position, to know where you are on Earth. It's worth taking a look at how this is done. So you are at the red point. What you are essentially doing is communicating with the satellite. The satellite is sending a signal. You are receiving a signal. You know exactly when the satellite has relayed the signal and when you have received the signal. Based on this, you can calculate the time difference. And once you know the time difference, you can calculate the distance you are from the satellite. But if you only have one satellite, you can have many points on a spherical surface where you are equidistant. But obviously, we're not in space. So what we do is we put a second satellite there, and we use both of these satellites in tandem. What this gives is a ring, a surface, where you can be anywhere on this ring if you use two satellites. But again, unless I'm Clark Kent and secretly Superman, I cannot be in space, so we know where we are. But this is a mathematical problem where the satellites do not know that I'm in space. So what we do is we put a third satellite, and we use all the three satellites together. So a combination of three satellites will give 2 points, 2 unique points where I can be at a given time. To resolve this ambiguity, we put a fourth satellite in space and use all four at the same time to pinpointly locate where we are on the surface of the Earth. That's how we know exactly where we are, and that's how something like Google Maps locates you and tells you where you have to go. So, some other fun examples. So in 1970s, early 1960s, there was a treaty that was signed between US, Russia, and I think UK, not to do any nuclear tests underwater, on ground, or in space. But what US did is they put a spy satellite so that no one is violating this treaty. So they launched a satellite to put in space that actually checks if anyone is doing any nuclear tests. So this satellite monitors radiation called as gamma rays. So gamma rays are emitted when you have nuclear explosions. And then this satellite is put up there to essentially track any nuclear activity. But what happened was this satellite ended up finding a signal. So in this figure, you see the zero line here. Zero means there's no radiation, but you see a huge spike saying that there has been some gamma ray emission. But fortunately, this has nothing to do with anything that's happening on Earth. This has been received from outer space, actually from another galaxy, not even our galaxy. These things nowadays are called gamma ray bursts. Nowadays, we know that they are associated with stellar explosions and stellar mergers. But this is a fun little example of how science happens by accident. And a few more things. Over the past 20 years, we've put multiple rovers on Mars to study Mars because it's much more easier to go there and physically study it. To put something in Mars, you have to launch something into space first. And then precision astronomy. It so happens that because of the presence of Earth's atmosphere, we can't study electromagnetic emission at all wavelengths equally. To study certain process or certain kinds of emission, we need to beat the atmosphere. One way to do that is actually put a satellite up in space so that it does not have to deal with any effects of atmosphere. These are two of the very deep field images of the universe. The one on the left is taken by Hubble Space Telescope. The one on the right is taken by James Webb Space Telescope, or JWST, showing thousands of galaxies in a single image. But enough with that. Now that we know why the motivation between why we put anything up in space, let's see how do we launch them. This does not come as a surprise to anyone. We use rockets, or more scientifically known as launch vehicles. If you look at this launch vehicle, this is over 100 meters long. A typical satellite is usually a few meters long. So why do we need this big vehicles to launch so small satellites? The answer comes from the amount of fuel that's required. So in order to put a satellite up in space, we need to beat the Earth's gravity. But it so happens that if you want to launch a satellite that's roughly worth 1,000 kilograms, you need fuel that weighs 500,000 kilograms. So in order to store such large amounts of fuel, you need large and long vehicles. So that's why rockets are built so big. If we look at how rockets actually work, this is the toy diagram. So what you have is payload that is sitting at the top. That is the only portion of the rocket that we use to launch vehicles. The entire rest of the body is used to store vehicle. That is used. Sorry. Yeah, good. That is used to store vehicle. That is used during launch. But how do they actually work? The principle behind them is very simple. It works on Newton's third law, which says that for every action there is an equal and opposite reaction. So what's the action and what's the reaction in this case? So the action is we have fuel and we have oxygen. You burn both of them together. That will release exhaust gases. And then you propel the exhaust gases with large velocities from one end. So that's the action part. So these gases, when they are propelled with such large velocities, creates large amounts of forces that will propel the rocket in the opposite direction. So the action here is the exhaust gases leaving behind, and then the reaction is actually the rocket moving the other way. That's upward. And depending on how deep you want to send an object in space, that determines how much fuel you need. So what we do is, in addition to the main body, we also have something called as boosters that we attach to the side of the rocket. So in this picture, you see there are two things attached, one to this side and one to the other side. They are called as boosters. Their sole purpose is to store fuel, launch the rocket, and then we'll see what happens next. So this is the time of ignition, where you see the main rocket engine and the booster firing. This is the same thing from a bird's eye view, where you can see the ignition takes place. And this is actually the ignition from the rocket. The exhaust gases are propelled in one direction, and the rocket is propelled in the other direction. This is a 5-minute exposure of how the rocket travels through the air. It takes this curved path. I know what some of you are thinking. We see rockets going straight up, so what's with this curved path? It so happens that if you look at the orbit of anything around Earth, the Earth is a spherical surface, and orbit is essentially a larger circle around it. So what happens is the object at any given instant of time is moving around this path, which is more or less parallel to the surface. So what you have is, you have your ground level, and in the final configuration, you have a satellite that's moving parallel to the surface in this direction. But during launch, you have a rocket that's faced vertically upward. The only way you can get from this configuration to this configuration is to take a curved path through space. So that's why usually rockets take this curved path. If you want to more precisely, a rocket starts here, goes up, and then it has, in this final configuration, has to move horizontally. So in the end, it takes this final curved path around the Earth. That's why when you see some of the rockets during launch, they are not vertical. They are always inclined to the vertical, because they're taking this curved path through space. Enough with the theory. Let's look at some actual videos. This is a compilation of videos showing rocket launches. So there you have ignition, and there you have takeoff. Not exactly. Probably, hopefully the next one. Yeah. So these are very initial stages where you are still experimenting with rocket launches. You have ignition, takeoff. Not again. Hopefully the next one. But you see what the point I was trying to make. So launching rockets is an extremely difficult job. Why is it? Because the very first step that involves rocket launching is a successful takeoff. But that in itself is very challenging, because of something called as unstable equilibrium. The initial configuration of a rocket is vertically up. It so happens that this configuration is unstable equilibrium. So if you take an object, and if you orient it, and if you disturb it, it rocks forward and backward, and it essentially comes back to its original position. But if you take it and if you put it like this, any small disturbance, if you topple it, it's going to topple, because gravity acts the other way. So if you have it this way, and if you oscillate it, gravity pulls it back. If you start in this direction and then topple it, gravity starts pulling it, and this becomes unstable. So that's why the starting point is very important in rocket launches. Any small disturbance to this initial stage can make the rocket topple. And these are the initial examples that I was showing of how some of the rockets failed. But once we have a successful takeoff, there are a few more steps before we successfully inject objects into orbits. And this process is called as staging. So what happens is, you have a large portion of rocket that's entirely fuel. But as you go up, you start burning this fuel. So the amount of fuel keeps on reducing. But the body that you're using to store the fuel is still remaining. That's essentially dead weight. So if you're getting rid of a container that's storing fuel, there's no point in storing the container as well. You might as well get rid of the container, because you're losing the mass, and the smaller the object or the lighter the objects, it is easier to propel with less amount of fuel. So what you do is, you design a process called staging. You take your satellite, you enclose it in protective casing, that's your payload part, and you divide the rest of the rocket into different stages, and these are your boosters. So as soon as you're done using fuel in certain part of the rocket, you get rid of that part. So you're losing the mass. You're reducing the mass, so you can propel something faster, and the process becomes more efficient. Let me show you an actual video of how this staging is done. So these attached things are boosters. So once you run out of the fuel, you essentially get rid of them. You drop them off from the rocket. So this is your rocket here, and yeah, showing the same thing. And once you do that, what you're essentially left with is rocket and a secondary engine. Yep. This is your rocket, this is your enclosing, and this is the secondary engine that is left. So once you're in orbit, you expel this protective casing, and then you detach the satellite from the secondary engine so that you can deploy the satellite into space. This is showing exactly the same thing. So the satellite that is being detached from the secondary engine so that you can launch into space. So just to give you a recap, what you have is you have your different stages. You take your satellite, you put it in a casing, you design your rocket for different stages. The number of stages increases depending on how far you want to propel. So if you want to launch something into Mars, you need more number of stages. But once you have the stages, you burn the stages, you get rid of the mass until you have the only remaining payload, which is the satellite, and then you put that in the orbit. But this rather seems a bit ineffective. It's like you buying a new car, taking your first ride, and as soon as the first ride is done, smashing the car into pieces or burning the car. You can't use it again. So in order to make it efficient, what happens to the boosters or the primary engines that you leave? They usually fall back into the ocean. They're collected, but they're never used. They're not in a usable state. So it's a bit, if you can use these boosters or engines again and again, the process becomes efficient. The initial rocket launches were usually $1 billion worth, every single rocket launch. Nowadays, they are a few hundred millions. Because nowadays, you can essentially use these boosters or main engines. So, sorry, just a minute. Oh. Yeah, so this is an example from 2015 where SpaceX did the first successful booster landing. So when the boosters actually are detached from the rocket, they fall with a great velocity, and landing them is extremely difficult task because of the large velocities involved. So it took a lot of time to figure out how to do a successful booster landing. So the first example comes in 2015, but I think most people remember this because this is latest. This happened. Oh no, one more technical glitch. This happened last month. Some of you have seen this video where you have SpaceX essentially catching the booster from the space. So you have booster that's coming back. It's slowing down. It has to fire in the opposite direction because it has to slow down. And then you will see a tower. It's essentially coming and docking into the tower, or tower actually catching it. You'll see that this booster coming, and then it precisely comes to where it is designed to come. This is a remarkable piece of engineering, an extremely difficult job. But this is with the solid rocket boosters or the primary engines. But as I've said, you have a secondary engine that is detached when the payload is in the orbit. So what happens to the secondary engine? That usually does not fall back onto the Earth, that stays in the orbit for a while. And what happens to the satellites when they run out of their lifetime? So if a satellite is designed for 5 years, it will work for 5 years. And what happens after 5 years? It stays in the orbit. So we have a lot of stuff that is out in the space and that is out in the orbit. Where are they located and how many of them they are? I'll invite my friend Leith so that he can very passionately describe what's out there.
Hello? Hello? Testing? Okay, awesome. All right, thank you, Akash, for taking us through the sort of why and how we send things into space. I'm going to dive a little bit deeper into the different kinds of objects that you'll find in our orbit. So imagine going outside at nighttime and looking up at the stars. And instead of just the twinkling lights, picture millions of objects, some as small as a speck of paint and some as large as a school bus, all whirling around our planet at incredible speeds. These objects are the remnants of humanity's exploration of space, and they're becoming a growing part of Earth's orbit. You can't actually see them with the naked eye, but they are there. So we're going to start by looking at the overall collective size and number of all these objects. So since the dawn of the space age in 1957, we have placed around 20,000 satellites in orbit. Of those 20,000, there are around 13,000 that are still in orbit. So many of them have either fallen back to Earth or have broken up in space. And of the 13,000 that are still in orbit, there are about 10,000 that are still functioning. So there are many satellites that are still intact but are no longer in use. Of the satellites that have broken up in space, we have recorded around 650 fragmentation events. This happens when satellites either just break up due to normal wear and tear. Sometimes satellites will explode if they have fuel leaks or battery leaks that catch on fire. And sometimes satellites will collide with each other or with other pieces of debris. And this creates even more debris, which increases the total number of objects in our orbit. If we look at that number 10 years ago compared to today, in 2014, we could regularly track around 16,000 objects in the orbit of our planet, and with a collective weight of around 7,000 tons. Now, today in 2024, we can track around 37,000 objects. And these are just the objects that we can track. So there are many that we can't see. We can only track objects like satellites that we have control of or very large pieces of debris. But it's estimated that there are actually over 1 million objects in our orbit that are larger than 1 centimeter in size. Now, 1 centimeter might sound small, but considering how fast these objects move, upwards of 16,000 miles per hour, just a 1 centimeter object can have 10 times the energy of a bullet. And the collective mass of all these objects is around 14,000 tons. And to help visualize that, that's about the mass of 3,000 elephants or 700 statues of liberty. Now, all these objects are spread throughout different types of orbits around our planet. This complicated diagram here shows all those different orbits. And you can see, I'll break down each of these more soon, but you can see for now that the densest part of the orbit is closest to the Earth's surface. So the Earth is in the center, and each white dot represents a single satellite or a single piece of debris. And you can see the Earth is sort of completely covered by them. So that area is known as low Earth orbit, and it's actually where around 85% of satellites live. And low Earth orbit is defined as being around 120 to 1,200 miles above sea level. And within low Earth orbit, there are multiple altitudes that satellites orbit called orbital rings. And it consists of cellular and internet constellations, such as Iridium and Starlink. And Starlink, so Iridium has been around since the 90s, but Starlink is a more recent development by SpaceX, and I'll talk more about that near the end of my section. But another aspect of low Earth orbit is that the satellites are close enough to the atmosphere that they experience a lot of drag, and this drag accelerates their decay in the process of them breaking up in space. And the largest group of satellites in low Earth orbit follow what's called a sun-synchronous orbit. A sun-synchronous orbit is where satellites, they pass over the north and south poles, and then they spiral around the Earth until they make one full revolution. And they make one full revolution every year. And this allows them to get constant lighting from the sun at all times. And so this is primarily used for imaging satellites for weather and spy purposes. But this type of orbit comes with some major hazards. Because all sun-synchronous satellites have to go over the poles, this makes the north and south poles very high traffic zones for satellites, and it makes them sort of the highest risk areas for collisions. And since these satellites move so fast, they have an average impact speed of around 25,000 to 30,000 miles per hour. So when satellites hit each other at this speed, it causes them to immediately shatter into thousands of pieces. This GIF right here models a satellite collision that happened in 2009 that created nearly 2,000 large fragments. Now, we don't just have internet satellites here. We also have things like space stations and space telescopes. So the International Space Station and the Tiangong Space Station are both here, and these are where astronauts will go to perform experiments that couldn't be performed in environments here on Earth. We also have space telescopes like Hubble and the Fermi Gamma Ray Telescope. As Akash talked about earlier, the Hubble telescope is used to take hyper-detailed images of our universe, and it's been used to make quite a few scientific discoveries, including verifying the rate of the expansion of the universe. And the Fermi Gamma Ray Telescope is currently surveying the universe for things like dark matter and supermassive black holes. So we've pretty much covered the basic things in low Earth orbit. So now we're going to look just beyond that. In this diagram here, you see the Hubble, ISS, and the Iridium constellation marked. So they're located in low Earth orbit. And then just beyond that, you see an orange band that's called the Inner Van Allen Belt. And that is the first of the Van Allen radiation belts. So these contain radiation from solar winds emitted by the sun that have been trapped by the Earth's magnetic field. So the Earth's magnetic field protects our atmosphere from radiation, but it still traps some of it in an orbit around our planet. And this radiation is very harmful to the sensitive hardware of satellites. So for that reason, this zone, the radiation belts, are a complete dead zone for satellites. So we have to look just beyond that, where we have the medium Earth orbit. This is where we find all of the navigation satellites that Akash talked about, like GPS. And this is a useful orbit for this is a useful orbit for navigation satellites because here we can easily make them have an orbital period of 12 hours. That means these satellites orbit the Earth exactly twice per day, which just makes them much easier to track and regulate. And if we look beyond the navigation satellites, we can find the geostationary orbit. This orbit, as you can see, there's another gap between the navigation satellites and the geostationary orbit. This gap isn't because of radiation, but it's because the geostationary satellites orbit the Earth exactly once per day. So the medium orbit orbits twice per day, and geostationary orbits once per day. So we just use it because it's very easy to keep track and regulate the satellites in this orbit. And the geostationary orbit mainly consists of communication satellites and satellites that send radio waves and television signals. And because it's so far out, the natural decay of these satellites can take centuries. So they'll be up there a while. And a fun fact, the idea of using this type of orbit for communication satellites was first popularized by the science fiction author Arthur C. Clarke, who wrote 2001: A Space Odyssey. He came up with this idea in the 1940s, nearly 20 years before the first geostationary satellite was launched. And so for that reason, we sometimes call this orbit the Clarke Belt. All right, now we have one more orbit to talk about, and it involves dead spacecraft. So dead spacecraft include satellites that have broken up or are no longer in use. It includes satellites that have intentionally been destroyed, which I'll talk about in just a second, and includes satellites that have been moved to what's called the graveyard orbit. So the graveyard orbit is just past the geostationary orbit. It's around 300 kilometers past, and it is where we move satellites that are no longer functioning just out of the way. And we do this because it's much easier to just push them a bit further out of the way than it is to bring them all the way back to Earth. That's way more time-consuming and expensive. So we typically, if we can, we just push them to the graveyard orbit, and we put them through a process called pacification. And that's where they will drain their fuel and their battery to reduce any risk of explosion. This picture right here is of Vanguard 1, which was launched by the US in 1958. And it is currently the oldest piece of space debris in our orbit. So even though the first satellite, Sputnik 1, was launched by the Soviet Union, that was only in orbit for about 3 months. But Vanguard 1 is expected to remain in orbit until around the year 2250. Okay, and now we'll come back to intentionally destroyed satellites. In the 1960s, the United States and the Soviet Union began their anti-satellite weapons testing program, where they tested missiles, not lasers, on satellites to just test their weapon capabilities. And they retired their respective programs in 1975, but around 10 years later, the United States relaunched their program, and they've done a handful of tests since. And in 2007, notably, China launched their first missile test that created more than 35,000 pieces of debris. And this is significant because it's actually the single largest space debris producing incident in history. And it's China's only missile test so far. But since then, in the years 2008 to 2021, the United States, Russia, and India have each launched a handful of satellite tests. And this picture right here is just of the path of the debris from the 2007 China test. And if we look past intentionally created space debris, we also have unintentionally lost debris from lost equipment from from astronauts aboard space stations. So, to go over some examples, astronaut Ed White lost his glove during the first ever American spacewalk. A spacewalk is when an astronaut has to leave their vehicle to, they either will leave to perform an experiment or do maintenance on the vehicle, and Ed White lost his glove to the vacuum of space. Other lost equipment includes Michael Collins and Suni Williams have each lost cameras in space, and so these cameras have photos that will likely never see the light of day. And other examples of equipment that's been lost. These are all, the next few examples are from Russian cosmonauts on board the former space station Mir. They've lost a thermal blanket, a wrench, and a toothbrush. So these are all objects that you can find if you look close enough at the night sky. Now, beyond the lost equipment, we also have discarded rocket boosters. Akash was mentioning how, if we can, we try to get these back down to Earth, but most of them break up or explode in space. And some of them remain intact, and they stay in space, and this can cause problems, such as in 1996, a European rocket booster collided with a French satellite, and this became the first ever recorded space debris collision. All right, and this pretty much covers the different types of objects that you can find in the orbit around our planet. So I'm going to look into the future a bit with the Starlink mega constellation. This is by SpaceX. It's a satellite constellation. Many of the satellites have already been launched. So in 2019, they launched a constellation of 7,000 satellites, but they have many more planned. So they have 12,000 planned to deploy, and that number might get extended to 34,000. So these are going to provide high-speed internet. And we have internet satellite constellations already, but nothing near this scale or this massive of a scale. And you might be able to imagine that this many satellites in orbit can cause some major problems. One issue that this causes is for observational astronomers. So this picture was taken by the Cerro Tololo Observatory in Chile, and as you can see, it has these white streaks going across the image. This was taken in 2019, not too long after the Starlink satellites were launched, and each of these white streaks actually comes from a Starlink satellite. So since they're not even close to being done launching these satellites, the problem is only going to increase, and it's becoming an increasingly problematic situation for observational astronomers. And this is just one of many hazards that these constellations could cause. But I'll pass things on to Lila to talk more about these hazards and the possible solutions. All right, thank you.
Can you hear me now? I think. No? Still not good? Can you hear me now? Okay, good. Uh, yes, so, okay, so we know that since the first satellite was launched in 1957, what we currently have is a cluttering ring of satellites, but also defunct satellites and fragments of collisions and remnants of space human activity in space. So we can wonder what will we have in a few years later. So it's predicted that around 60,000 space objects will be in a low Earth orbit greater than 10 centimeters in size by 2030. So we can ask ourselves if there is maybe a limit of how many objects can we put out there, and if there are any consequences to have that many objects in orbit. So this can have an individual object can be inoffensive, but however, the sheer volume can be cause of concern. And because this can give place to what is known as the Kessler syndrome. So the Kessler syndrome involves 3 stages. So in the first stage, what is more or less what we currently have. So we have millions of pieces of debris in orbit, greater than 1 millimeter in size. And then, as was saying, they travel at very fast speeds. So chances of collision are high. So in stage 2 is when these satellites start colliding, so creating more fragments. And this, at the same time, increases the chances of more collisions. And so this can go on and on. So in stage 3 is when there are many collisions, and it can happen like a chain reaction that cannot be controllable. So at that point is when we reach the Kessler syndrome. And so this can have some effects. But before going to that, I will show you this is just a video. Sorry. It's a video of what happened when the collision happened between the 2 communication satellites, Iridium and the Russian satellite Cosmos, that already Leith talked about. But we see how many debris objects happen after this. So these objects, they remain in the orbit of the Earth, but then because of the collision, the orbital plane can change, so the collisions can happen in any direction. So, and because these are not the only objects that are there, this increases the chances of collisions with pre-existing objects. So we've seen that this is an increasing problem, and we are seeing already some effects. So this is just an example of what happened to the International Space Station window. This is a photograph of an astronaut who took when a small object, tiny object, collided with the window with the ISS. And we are seeing this more frequently and more recent events. So just in June this year, a Russian satellite broke up in space and then forced the astronauts in the ISS to shelter and to adjust the orbit of the ISS. And in July, it was a breakup of a defense meteorological satellite, and it created 5 more pieces of debris. In August, a Chinese rocket broke up apart just shortly after launch, creating hundreds of pieces of debris. And just last month, an Intelsat satellite broke up, creating a few tons of space debris. So we are seeing that this is increasing, and with this also the chances of the Kessler syndrome is a growing possibility. So we need, before going to what we can do, we are going to see the effects. For those of you who have already seen or watched the Gravity movie, this is, if not, this is just a short spoiler. So you can see how a tiny object collided with the vehicle of this astronaut, putting in danger the life and the space travel. and of the astronauts, and we see how these objects start colliding with nearby satellites. And so these are some effects that these kind of collisions can happen, putting in danger of creating a major risk of security among civilian, military, and commercial infrastructure providers. So we need to, so we can see that there is some threats to both current but also previous missions, and also the global security and economy. So we need to do two things. So one is stop polluting, and second, we need to remove the garbage in order to keep the space a reusable resource. So the first way we can do that is by mitigation. And with mitigation, it involves redesigning satellites. So we need to create reusable rockets, like this example of SpaceX, but also maneuverable satellites. So the satellites need to have a little bit of fuel in order they can be moved in orbit after launch. We need also to create protected regions in space that is adopting a specific spacecraft altitudes for different kinds or types of satellites. And also mission planning in order to safely disposal and also to be more easily removed from orbit. So we are seeing here just an animation of how in 200 years your low Earth orbit might look like if we don't do anything, we keep the business as usual. And the difference we see if we implement these kind of measures. However, we see that even implementing these measures, the number is still increasing. So we need to manually remove the garbage. But before going to that, the second way we can keep the space a reusable resource is by tracking and measurement. So the tracking is to keep track of where the where the satellites are in orbit in order to avoid collisions, but also to keep a good space traffic. And also to adjust the trajectories in case of a possible collision. For doing the tracking, the U.S. Defense Department has this space surveillance network, which can actually track the satellites. And for doing that, they use both radio and optical telescopes. So here in this map, we see all the different resources they use. And for radars, they use tracking radars, detection radars, or imaging radars. And for optical telescopes, they use both space telescopes and ground-based telescopes. But while looking at this, I just came to this website, n2yo.com. So if you actually want to know how many of satellites are above of us right now, you can actually scan this QR code, and you can give your position, and you can see how many satellites are above us just right now. And this website, they actually can track almost 30,000 objects already. And another way is by measurement. So actually, they can take their returner hardware that reaches to Earth. It can be of great information and tell us the directional distribution and composition of debris flux that is out there. And so the third way that we can keep space a reusable resource is by deorbiting the defunct satellites. By deorbiting, it means that they will enter the lower Earth atmosphere and they will burn up. So small satellites will fully burn up, but the bigger satellites, like the previous image, won't be fully burned up. They will reach the Earth. And so, however, as we previously see, not all satellites can have the fuel so that they can come by themselves to Earth. So we need to come by some actions in order to actively remove the debris. So how we can do that, it will depend on the size of the object and how far they are from Earth. So these are all these different types of ways we can do that. However, here I will just quickly mention or review 3 of these ways. One is by using electric tethers. Second is by using space lasers or collector satellites. So I just want to mention that these are under development and on testing currently. And so scientists and engineers are working on this kind of projects. So first we have the electrodynamic tether. So for this, what we have is we will have a small satellite that will have a tether, an electrodynamic tether, and this will latch into the debris object. So since we have an electrodynamic tether that is traveling through the electromagnetic field of the Earth to high velocities, it will produce a current that will interact with the magnetic field of the Earth, producing a force that will drag the object back to the Earth, and it can be deorbited. And so second, we have laser brooms. So it could be either ground-based or space-based. For the ground-based, we will have a radar that will first locate the object, and then it will track it so that we know where the laser can be pointed at some point, and then it will inject some energy to deorbit this object. So in the case of the space-based lasers, they act in a similar way. However, they have some advantages. So the angles, they have more favorable angles, and the distance are shorter. However, they are more difficult and more expensive to maintain compared to ground-based ones. And last, we have collector satellites. So also satellites, scientists and engineers are working in creating these small satellites that can travel and grab the debris objects in space. And they can either drag them down or push them to other orbits or to the graveyard. And also, a more innovative way is by using space nets that they will mimic the way in which the fisherman acts. So they will launch the net to this space object that is moving freely in space from some distance, and then it will drag them down to the Earth or push it down to the graveyard. So to summarize, we have 3 ways. 3 main fields of space sustainability. So one is the life extension services, so redesign the satellites and make reusable rockets and all these kind of things. Then we have space situational awareness by tracking and measuring satellites. And third, we have the active debris removal. So, but looking at the future, so what we need to do is to innovate in technologies, so create more efficient, reliable, and cost-effective deorbiting solutions. We also need integrated satellite design. So we need to integrate deorbiting technologies as a standard feature, no matter the size and the type of the satellites. And also, we need to come with binding treaties. So discussions are ongoing about the creation and enforceable regulations because it is important. Existing agreements are mostly voluntary in everywhere in the world. So we need to come up with global collaboration among different countries and organizations in order to develop and implement global deorbiting strategies. And this is just something that I hope it doesn't become a reality, that in 50 years our sky will look like this. So thanks so much for listening.